Good afternoon, Professor.
Good afternoon. And now
Good afternoon, Professor.
afternoon. It's like the Savannah Caroline duet chorus sequence. Good afternoon, good afternoon. And good afternoon, Jose. Good afternoon, Amanda. Good afternoon, Caitlin. I'm now going to chat. Good afternoon, Rashman. I'm going to chat. Oops, someone's here. My dog is. Who let the dog? Okay. That's a song. I didn't mean it like that. Okay. Hello. Hey. Oh, and the thing just okay. Hello. Hello, Azra. Good afternoon, Stephen. Good afternoon, Caitlin. Good afternoon, Amanda. Good afternoon, Adan. Good afternoon, Mackenzie. Good afternoon, Dave. Good afternoon, Evan. Wait, someone else is here, or is it someone? Sorry. Good afternoon, Erini. Good afternoon, Jose. Good afternoon, Erica. Hey, Douglas. Good afternoon, Estrella. Good afternoon, Rashman. Hi, you've been on my board. Okay, let's get this already started. Excuse me. Oh, and Katya's here. Okay. We actually have a lot to do. Oh, we actually have much to do. I forget. Yeah, all right. We're just gonna get rolling. Oh yeah, so quickly. Oh, and more people are coming. Yeah, just so we're still in the context, we're still backing up and doing all this math. The next homework assignment has been posted. It is due a week from today. Like it's not due month, you have 2 class sessions to do it. It's long. It's about a lot of this math that we're doing now that and some math still that we haven't still done. It's got the dot product involved at the end. It's got reminders of, or to recall, review, refresher for you of taking derivatives, which I am assuming is sort of comfortable for many of you. But I am assuming you're kind of okay with taking derivatives. But the homework refreshes some of that, and then it's all leading towards, all of this is leading towards question 9 on homework 1B. But and today we're going to do more of this integral calculus math stuff, all of which we need for the rest of the course. But the long way of saying, yes, there's a new homework that's due next Wednesday, but that does not mean that you could still turn in updates, and I will still turn in updated feedback on homework 1B. I've noticed a couple people have submitted a couple of drafts, and they just got more and more points each time they submitted a draft, even if I gave very limited or to none feedback. So the door is not closed on homework 1B, but we are moving on in terms of what's due next week is homework 2. Oh, and good afternoon, Amy. Awesome. Okay, Amy C, that is. So let's just get rolling here. Okay. Hold on, just a minute. So yeah, as always, just stop me if I'm going. Hopefully you saw in the Google Classroom, you totally get points if you politely tell me to speed up or politely tell me to slow down, either way. But here's where, let me just fix the view on this. Here's where we, okay. Picking up where we left off on Monday. Again, we've gotten the answers to question 4 and 5, and I think most of you probably can do questions 6, 7, and 8, or did 6, 7, and 8 on your own without too much difficulty. All of this underlying stuff that I'm doing is all to lead us to really understand the final question, number 9. But anyway, I'm trying to unpack or define and compute what we really mean by work in physics. So, and our goal, oh yes, okay, here I see what I'm saying. My goal in all of what I'm saying today, my goal is to show you that work in physics is actually defined to be something that we refer to in mathematics as a path integral. Specifically, we're trying to show that work is the path integral of force. That's all of the, and I'm trying to show that. I'm trying to show what that means. In part, these 2 days that I'm doing, in part, is meant to show you in a slightly maybe more deep way what work, what the physics concept of work is. I'm trying to show you in a more deep way by referring it to some more precise mathematics. So that's one way you could think of all this, is I'm using math to explain more deeply what a physics concept is, or perhaps more likely and perhaps more applicable to many of us, I'm using a physics concept that you have some familiarity with in order to really show you what a certain math idea is. So by the end of today, I really want you to have some kind of understanding of what an integral is in general. I know you've used them. I know many of you have used them. I know many of you have solved many problems where you integrated. But if you're at all like me, then you may have done a lot of integrating problems on a lot of exams in a math class, but you may have at some, well, I can't say what you're like. What I was like for like at least 3 calculus classes and at least 2 physics college classes, anytime I had to do an integral, if they set it up for me and told me do this integral, I could maybe do it, but I hated it. I didn't know what I was doing. I was just following procedures, and I knew it. I did not understand what the procedures meant. I didn't understand what the integral had to do with anything. I didn't understand where the integral was coming from. And if God forbid in a physics class, quark forbid, in a physics class, they would do a problem where I looked up the solution in the back of the book and it said like, oh, to solve this problem, you have to set up this integral and then solve it. I'd be like, well, okay, then it's over because I have no idea when I'm supposed to set up an integral or why or how or what an integral means. I'm just telling you where I was for at least 3 classes of calculus and 2 of physics. And by the way, I was a physics major. I mean, I was like signing up for all of this, and integrals just, I knew they were super important and I knew they were coming up all the time, but I had no idea really what was going on with them. Unless you specifically held my hand and said, do this integral now, use integration by parts or use substitution to do this, then I could like do it, but I had no idea what it was that was going on. To be more specific, I knew that an integral always had to have like a dx or a dy or something like that in the expression. But as far as I was concerned, the dx or the dy was just like part of the squiggly symbol. They just were like this package of symbols that told me that it was an integral, but I never knew what to do with the dx or the dy or where it came from. And it just seemed like it always just disappeared magically when I got a solution. So it all just seemed like this black box to me. Now, again, I'm not saying that's true for all of you. I think it's probably true for some of you in my experience, but I don't know who, but I'm just saying that was true for me. So even though I, like you, was required to take calculus in order to do physics, it turns out for me, it took years and years of seeing the calculus in the physics to actually go back and understand what the calculus was all about. So I'm going to try. So today, I'm going to try to continue in this discussion of like showing you what we mean when we say that work is an integral. And my goal is really to maybe start us afresh and show us what an integral is in the first place. Okay. Now, I'm going to say one last thing and I'm going to go back to where we were. The best way to try to listen to me is if you don't think you like integrals, if you've had a bad experience with integrals or you're not clear on them or you're scared of them, then please do listen. This is for you. I'm not assuming you're in command. If you're scared of them or don't have then fresh slate, we're starting from scratch, like clear your mind and let's start again. If, however, you think you're already down with integrals and if you think you already get integrals or are good at them, then don't tune out and try not to be bored. Be relaxed since you already feel comfortable with integrals and see if this doesn't give you some other different, possibly more physics helpful, scientifically helpful perspective on them. Okay, I'm just telling you again. See, this day, every time I look at an integral, I see a new, deeper level that I didn't see before. I don't think it's a one-off integrals. So I think hopefully you can benefit from this no matter who you are. All right, so what we were just saying 2 days ago, so I'm in the middle of the page now, looking at this part of the page where it's circled in red. Where we left off is 2 days ago, we said, if you push something or pull something for a little bit of displacement, a small but finite amount of displacement, then the work you do for that small but finite amount of displacement is defined to be the dot product of how hard you pulled or pushed with how far the displacement was. And dot product basically means the multiplication of the two vectors, but only to the extent that the two vectors are lined up with each other. So a dot product really means the multiplication of the portion of one vector that is parallel to or lined up with or projecting onto the axis of the other vector. It's the multiplication of the common components of two vectors. So if you do work for a little bit of a small but finite amount of displacement, we say that the work you do is the force applicable to that displacement times the displacement itself. That's what we say the work is. Okay, that's what we said 2 days ago. So we had to figure out what a dot product is to do that, but we did. So that's what a small but finite amount of work is. Then we said, okay, what do we mean by small but finite? I mean, we're saying this only applies, this definition only applies if you exert a force through a small but finite amount of displacement through space. It only works if it's small but finite. What do we mean by small but finite? Well, finite means countable, measurable, quantifiable, greater than zero, right? Finite means above the threshold of measurement, like our measuring tools can pick up a number for it. That's what I mean by finite. And it doesn't go on forever. By small, what we said was small means that the small delta x is small but finite, we mean that it's small enough to keep f from changing. It's small enough that f, that f is a constant, f naught. That's the definition that applies for the small but finite case. So then we said, okay, what do we do in a large case of delta x? What do we do if delta x starts getting really large? Large enough that f starts varying or changing, large enough that you have a different f for each little chunk of delta x. What we said is, in this case, we can deploy the concept of superposition to compute and define W, the total work. Again, please notice again, all we've defined so far with our dot product and everything, all we've defined in the middle of the page is delta W, a small but finite amount of work. If we want to know work in general, we're going to deploy the concept of superposition. What do I mean by superposition? Superposition is the concept that the whole is equal to the sum of its independent parts. This is worth pausing on for a moment in physics. Like all great ideas in physics, hopefully, it sounds totally obvious once we say it. It sounds so obvious, like the whole is equal to the sum of its parts. It sounds so obvious that it feels like it shouldn't even need to be said. But like all great ideas in physics, the part that isn't obvious isn't the statement itself. The part that isn't obvious is that this seemingly obvious statement leads to other surprises. Specifically, what I mean is superposition is the name for the concept the whole is equal to the sum of its independent parts. The reason we give a name for such a seemingly obvious idea is because, in fact, the idea isn't always true. It isn't always true in life. There are a lot of legitimate cases in life where this concept does not apply. And there's a lot of legitimate cases in physics, specifically this course of physics, where this concept does not apply. I would argue the opposite of superposition, sometimes you can call interaction, or more specifically, interference. What I mean, the key is the word independent here. When we say that the whole is equal to the, so I'm going to pause for a second and tell you that sometimes superposition is not true. It is true here, but it is worth noting the idea, like why we have to point it out at all, because later on in this course, there's going to be a case where it's not true. When we say the whole is equal to the sum of its independent parts, we mean that each part makes a contribution to the whole, and you add up all the parts and you get this whole, but that each part, what it's contributing to the whole, is not in any way affected by the presence, by the existence of the other parts. When we say superposition, what we mean is that the parts don't interact with each other or interfere with each other and thereby cause some other phenomenon to come into the mix. In real life, for example, oops, someone's here. Sorry, hold on. Okay. In real life, this is not a physics example, but just a quick real life example. Let's say I can grade 5 papers in an hour, and let's say Professor Walters can grade 10 papers in an hour. Okay, like I by myself can grade 5 papers in an hour, and Professor Walters by herself, like independently of me, could grade 10 papers in an hour. If you put so say you now want to grade some papers, so you put us together in a room to grade papers for an hour. If superposition applies, if the whole is equal to the sum of its independent parts, if the parts continue to function independently and make their contribution to the whole, that would mean that if you put Professor Walters and me in a room for an hour together, we would grade exactly 10 plus 5, 15 papers in that hour. That's if superposition in fact applied. Honestly, in real life, in this like sort of dumb example that's not really physics, but in real life, I don't think superposition applies. I think I can grade 5 papers and she can grade 10 papers. But if you put us together, if you make us parts of a larger whole, we're going to interact with each other. There's going to be my 5 pace and her 10 pace, but there's going to be this extra element of the fact that we're going to talk together and maybe slow each other down by talking, or maybe give each other hints and tricks and techniques and help each other out and speed it up. We're going to interfere with each other, perhaps destructively or perhaps constructively, but there's going to be an extra element that comes into play just by fact that we're both there as part of a whole. That is called interference or interaction. And it can happen in physics, like when 2 wave pulses hit each other. The total energy of the 2 wave pulses is bigger than or smaller than, depending what you would get if you just added up what you would get from one wave and the other wave. So sometimes in physics, especially in this course, things don't superpose. So it's an important concept to know about. However, with straight up forces and straight up displacements, superposition does apply. So if I want to know, okay, that's like, so superposition applies. I believe that when it comes to the work done by forces throughout space, I believe that the whole is equal to the sum of its independent parts. So if I want to do work throughout some long displacement, long enough that the force is changing throughout that displacement, I believe that it makes sense to say, I only knew how to I only know how to compute work when I have a given value for force to multiply by some small displacement. But here I'm looking at this large displacement where the force keeps changing and changing. So what I can do, what I would do, is divide the whole displacement into a lot of little chunks of displacement, a little small but finite chunks of displacement. How small would you divide them, Yaverbaum? I would divide them into sizes that were, I would pick a size of portion that was just small enough to no longer see any change in the force. So if I had a 100-meter long displacement with a force that kept changing every 5 meters, I would divide the whole thing into chunks of 5 meters each. I would I would walk the first 5-meter chunk, and I'd say, what's the force here? It's 100 newtons. Okay, thanks. So I would take the 100 newtons, dot it with the 5 meters of displacement. I would take the 100 newtons of force, dot it with the 5 meters of displacement, and get, say, I don't know what the angle is, but say I get 500 joules of work. I'd put that in my bag. Then I'd walk to the next 5-meter displacement. At this displacement, say the force is 200. So I would calculate the work for this little displacement. 200 times 5, okay, that's 1,000. I put that in my bag, in my mental bag. Then I walk to the next step. 5, now the force is, say, 300. So now it's 5 times 300, 1,500. I'd add that to my bag. So I would just go piece by piece by piece. And I would say, in the end of the day, the fact that the force was, I would say, at the end of the day, I know how to calculate work as long as I have one number for force. I don't know how to do it if I have lots of different numbers of force, except, what I'll do is take the whole total and divide it into lots of little pieces for each of which has one number for force. And I'll just add up all the results. I'm just saying the most, in a way, obvious thing in the world. I'm saying the total work for a large displacement would be the sum of all the little constituent works, each of which has one assigned force, right? The whole is equal to the sum of its parts. Now, I'm going to write that mathematically, which I think I started to do, or I did do on Monday. But to write that mathematically, I use the mathematical symbol for sum. And my board disappears. Hang on, my board's disappearing. There goes my board. Even though I just, yep, okay, hold on. Okay, there it is. Oops, there it is. Oops, there. Okay. Okay. And again, this is the Douglas point. I'm going to write on this so that the Douglas. Also known as Alex. Okay, anyway. So now look at the black on the top. The black big sigma, just literally me. And again, you might think, like me, the minute you see that sigma, you might be like, oh, vomit. I was like kind of with him when he was yammering around, but now all this crazy math goes. It's not crazy math. It's just literally a piece of notation to symbolize what I just said in English. That big jagged symbol is a big capital Greek letter sigma. We use sigma to mean sum, as in S-U-M. And we specifically use that type of sum symbol when we are adding up a bunch of things, excuse me, that are, when we're adding up a whole collection of items that are divisible, that are discrete, that are bounded, divided from one to the next. In other words, when we're counting up, when we're adding up a whole bunch of items that are countable, where you could literally, like in this, well, yeah, when we're adding up, when we're doing what we call a discrete sum, where we're adding up a bunch of items that you could tell the difference, the distinction, the division between one item and the next, when you could literally be like item number 1, item number 2, item number 3. In other words, like grains of sand, even if they're super small, you can still tell the difference between one grain of sand and the next, as opposed to just a smear of water, let's say, where you can't even tell where one bit of water ends and the next begins, like unless you have an electron microscope or something. So this symbol sum means sum over countable items. And then what we literally do is count, right? We set an index, a counter index called lowercase I. We started at 1. We say, okay, we're going to start at the first item. I equals 1. We're going to start at the first 5 meter, the first displacement of 5 meters. We're going to look at what force number 1 is for that first 5 meter chunk, right? We're going to set I equals 1. We're going to say what's the first force that we're looking at for that first 5 meter chunk. Oh, it's 100. Okay, so we're going to multiply the first force, 100 newtons, by the 5 meters. Notice I don't have an index after the delta X. Like you could put that and it wouldn't necessarily be wrong. But the reason I don't even put, I mean, I could put one there. Maybe it's better. It's a judgment call. But the reason I don't put the I on the delta X is I want to emphasize to you that each delta X is the same. I've divided my whole journey into a bunch of equal spaces, 5 meter, like small enough so that I can capture a countable number of different identifiable constant forces, right? So I go to the first 5 meter chunk. I look at what the force is for that, say it's 100 newtons. I multiply them together. I put them in the bag. Then I tick the counter. I go to I equals 2. So I go to the next 5 meter chunk. Again, it's 5 meters again. So that's why I'm not putting another I on it. It doesn't matter. Like it's 5 meters again, but now I equals 2. So I look at the second force. The second force is 200 newtons. So I multiply those two together. I dot product those two, put it in the bag. Then I go to the next number 3. And I'm literally using I as an index for counting. This only works if I could literally count up all the chunks. And it might be a really, really big number. But again, what I mean by count is I can separate them Here's a 5 meter chunk with a particular force applied to it. Here's another 5 meter chunk with a different force applied to it. Here's the next 5 meter chunk with a different force applied to it. And I add them all up until I get to n, lowercase n. Supposedly n is the number of pieces, the total number of displacements that I divided this whole journey up into. It's the number of different forces that are applying, right? So what I'm saying right here so far, I'm saying a little bit of work, I mean, a small but finite amount of work is a force dot product did with a small but finite amount of displacement. If you want to know the total work done over a huge displacement, a displacement that's big enough to allow for many different Fs, then many different forces, then you divide the whole thing up into the number of Fs that there are, and you go through one at a time and do a dot product for each different F and add them all together. That's what this is saying. That's a procedure for computing work over a large but finite displacement. We would be done, right? Hopefully that makes sense. Just looking at the time. Okay, does that make sense so far? Or actually, yeah, just hold on. I'm going to change the view for a second. I mean, oh, thank you, Savannah. Okay, that's what I was just, and thank you, Caitlin. Okay, and I know it's not fascinating, but it makes sense. Okay, I'm going to take those two. Okay, good, fine. So it makes sense so far. So maybe it's not interesting, but there's at least two people are saying it makes sense so far. Now, where am I going with this? Well, I'm saying that the problem is this is all fine, but this is all assuming that life works like a cartoon. This is all just saying work is the sum of its parts. But in real life, things don't divide up into parts like this. What I'm saying is, well, yeah, I'm saying this discrete sum, the jagged, that sigma is what we use in math whenever we are considering a discrete sum, a sum of elements that are countable, divisible, discrete, distinguishable, however you want to put it, chunky. This applies to chunks. But in real life, in the lab, in nature, in space and time, things don't generally tend to change in chunks like this. Like, wait, I'm just looking at what I wrote here. This discrete sum accomplishes our goal of computing total work if and only if. IFF means if and only if, okay? This whole thing that I'm saying so far works if and only if the force varies as a discrete or step function of position. Like, this all works as long as whatever force you're talking about, if you were to make a graph where force were on that y-axis and displacement or position were on the x-axis, if the force were changing in steps, if it looked like a step function, then this would all work. But that doesn't generally really happen in life. What we care about more realistically is, what if force varies as a continuous function of position? What if force varies continuously? What do I mean by continuously? I mean, what if the force varies in a smooth or infinitely divisible way, right? In other words, what if I'm trying to use this method? So I look at the situation and I'm like, all right, clearly F was changing over this whole 100-meter displacement that I'm looking at. So, okay, so I'm going to divide it into little intervals of 5 meters each and hope that I've got one F value for each 5 meter. But I look at each 5 meter little section, and even in the 5 meter section, I notice F does not hold steady. F doesn't vary from 100 to 2. I mean, yeah, like maybe F doesn't vary all the way from 100 to 200 in 5 meters, but it seems to vary from like 100 to 110 newtons or something like that. So then I go, okay, wait, I didn't divide into small enough segments. Like, I'm still making my segments big enough that F is changing. Let me go down smaller. So I go down to a meter. So now F varies less, like it doesn't have as much room to change, but it's still, I notice F is varying from 100 to 101 newtons if I go to a meter. Then I go to a centimeter and F varies less, but there's still a range of values for F. A perfect example of what I'm saying, this is not hypothetical. The spring that we're talking about in homework 1B, right? And that you looked at in the lab for at least a week. Yeah. The spring is exactly an example of that. Hooke's law for a spring is F equals negative KX. That means no matter what value you put in for X, we spit out a different F. If you change X by 0.0000001 millimeter, then F changes by 0.00001 times K, like whatever K is, right? There's no, you can't find a finite interval on that spring. If you're that mass going back and forth on the edge of that spring, you cannot come up with a finite number that is small enough to capture a constant F. F is continuously changing. Continuous means without division, that any 2 points of any two different F values have no gap between them. You can always, if F here is 100 newtons and then here it's 101 newtons, you can definitely find a place where F is 100.5 newtons, and so on and so on and so on. Continuous means infinitely divisible, right? So it means that what we want to do, if we want to do this right, I don't know how to do what I'm about to say. I mean, I do, but like what I'm saying is that what we want is, if we want to compute work for the case where the force varies as a continuous function of position, such as the spring force, we're going to want to take a sum of force times displacement in the limit as the delta x approaches zero, right? What we really want here is to divide up our whole larger displacement, not just into a bunch of small but finite delta x's, but into a bunch of infinitely small dx's, right? That's what we want. I'm not saying I know how to do it yet. Please stay with me. Don't worry about how that can be done. I mean, I'm going to tell you, but right now I'm just saying, does it make sense that what we want, if we want a perfect value for work in any case where the force continuously varies with respect to position, if we want an expression for work in a case like that, we would have to take the sum of force times displacement in the limit as the displacements went to zero. We wouldn't want a sum of F delta x's. We'd want a sum of F dx's. That's what we want. And when we do, so that's what we're going to do. Now, when we do that, when we take the discrete sum, hold on, I'm switching the view again. Sorry. When we take the discrete sum, the discrete, choppy, plucky, countable, divisible sum known as sigma of F delta x, and we go to the limit, where now all the delta x's have been smoothed out and they're all continuously one on top of the one next to the other. When we take delta x to the limit as it approaches zero, we change delta x to a dx. That's what I'm saying. We change delta x to, oh, sorry, this is a mistake. Wait, sorry, there is a mistake here. Hold on. This should be, whoa. Okay, I am saying that when we go to the limit, when we change from a discrete sum to a continuous sum, we change our delta x's to dx's on purpose, because that's what we're doing. We're still multiplying force times displacement, but now the displacement is infinitely small, so we change the delta x's to dx's. And in order to capture that idea, in order to not have to write out limit every single time, to capture the idea that we've changed from a discrete, jagged, countable, choppy sum to a smooth, continuous sum, we change our sigma to a smooth, elongating, graceful S, which is the symbol for integral. I'm saying, by definition, the integral from point x1 to point x2, the integral of f dot dx is simply equal to the sum of f dot delta x's taken to the limit as delta x approaches 0. The integral is just the limiting case of a discrete sum. An integral is a sum. The integral sign is an S. I didn't know that until at some point I did. But I did about 1,000 integrals. I did hundreds of integrals with just copying that sign and having that dx just sitting there, having no idea that the entire time the reason we was using that sign, that squiggly integral sign, that thing is an S. It just stands for sum. But it's nice and smooth and graceful because what we're trying to tell ourselves is we're summing over a smooth, continuous interval. The work integral is the continuous sum of dot products between force and displacement. Any integral at all will always be a continuous sum of products. That's what an integral is. It is simply a discrete sum, a sum. It's just a counting up of chunks taken to the limit where the chunks are infinitesimal or infinitely small. I'm going to go one step further. So, but again, right now, my point is the integral is the continuous sum of products. It is always a continuous sum of products. What is the product always in an integral? It is always, well, in this case of work, it's a product, it's a dot product of a little bit of displacement times a certain amount of force, right? That's what we're talking about here. Displacement times force, displacement times force, displacement times force. But the whole assumption here, the whole reason that we're doing all this is because we assume that force is some function of displacement. Again, think of the spring, F equals negative kx. The whole idea here is that we're taking a situation where if you tell me where you are, I can tell you what the force is. And that's good and bad. The good news is, tell me where you are. I can tell you what the force is. The bad news is that anywhere you are will generate a different force. So if I want to add up all the force times where you are, that's a little bit tricky because every different place you could be has a different force. The point is that where you are, displacement, position, space, x, is an input. It's the independent variable. And what we believe is that there's some rule, in this case, F equals negative kx. There's some rule that maps your independent variable, your input, to some output, some dependent variable known as force. We believe there's a rule, there's an equation. We believe here that force is a function of position. This is the way, so we say, what we say is, to calculate work, we want to do the continuous sum, the integral of force times displacement for every little infinitesimal chunk of displacement you go. Every little displacement is the input, every bit of force is the output. This is the way integrals always work. Every single integral, if f of x, if y is some function of x, then the integral of f of x dx always means walk a little bit along the x-axis, investigate an infinitesimal little change in the independent variable. In that little, like you're walking such a small amount that you can believe there's just one value of output of dependent variable of function for that independent variable. So you walk a little bit in the independent variable, ask, what's the dependent variable here? Like you walk a little bit in x and you ask, hey, what is the value of f of x? Oh, it's that, thank you. And you multiply the two together and you throw it in your bag. And then you walk a little bit more on x, say, hey, now what's the dependent variable? What's the output? What's f of x? And they go, it's, and you say, thank you. And you multiply the f of x times that little value of delta x that you, or dx that you just walked, and you throw it in your bag. And then you walk another little dx ask the new value of that, and you multiply them together and throw it in your bag. This is why people in calculus classes say that the integral is like the area under the curve. Because sure, yeah, you're dividing up the area under the curve into all these little rectangles. The width of each rectangle is always the same. It's the little bit that you're walking along the x-axis, the little interval in independent variable, and then you're multiplying it by the height, which is the value of the dependent variable, the output. So an integral always is a continuous sum of products. The product is always the input times the output. That's all it is. And that's why the little areas of rectangles, it's input times the output. The simplest version I know. So an integral is always it's just a sum of products, but it's taken to the limit. It's continuous sum. So the product is always the function times the function of x times dx, the infinitesimal little advancement in the x variable. The dx is not just there for no reason. It's what we're actually calculating. So an integral is always a continuous sum of products. The product is always the input times the output, or it's always an infinitesimal advancement in the input times the output. In the case of work, the input is displacement, the output is force. So it's a continuous sum of products of displacement with force, okay? So either right now, I'm telling you, an integral is always a continuous sum of products. If you want an example of what I mean, think of work from physics. Or if you think you already understand calculus, then I'm telling you the way to think about work in physics is think of it as the most basic example of an integral that there ever was. Work is the classic, it's like the reason we practically the reason we ever made up or discovered integrals. Work is a pure, great, vivid example of an integral. Now I'm going to be more, okay, so it summarizes that here. So the integral is the continuous sum of products, and the product every single time is an infinitesimal interval along the independent variable with the corresponding value of the dependent variable. Always, like that. The two things that you're multiplying are an infinitesimal interval along the independent variable, like usually x, along with the corresponding value of the dependent variable, f of x. Okay, that's what an integral always is. But I'm going to say it one more time. Please forgive me. I'm saying, if anybody, you're walking through the forest and some very strange forest, and somebody walks up to you and is like, "Hey, what's an integral?" Say it's a continuous sum of products. That's what an integral is, triple equal sign. None of this has anything to do yet with how you compute it. None of this even means that it can be computed. I don't even know if an integral can be computed. I don't know if I can do the integral of negative kx dx. Maybe I can, maybe I can't. I don't know that yet. I'm just saying this is what, if I could do it, it would tell me the work done by negative kx. Also note that I have not yet, okay, this is a little bit obnoxious what I'm about to say, but notice that in nowhere in here have I said anything about antiderivative. I will eventually use the word anti. I mean, we'll get to that like very shortly, but I want to be really clear here. That's another point. Like, and if you don't know if the word antiderivative is not in your mind, good, keep it out of there. But if it is in your mind right now, kick it out. Because I'm saying what the integral is a continuous sum of products. That in and of itself has nothing to do with derivatives or anything. The dx in the integral is a differential, right? It's an infinitesimal difference. It's all it is. No one is saying anything about slopes of tangent lines or instantaneous rates of change or anything, or rates or any. This is not anything about derivatives. This is just a thing unto itself called an integral that exists on its own, that if I could figure out how to solve it, I'd be psyched, because then I would know how to compute the work done by a spring, okay, on a mass. So that's that so far. Now a little bit more. And I shouldn't just always talk to Doug. So okay, I'm just writing to keep this board alive, and I always say hello to Doug because it was his idea, but I don't want to so I'm saying hello, Caroline. Whatever, it's just random. Okay. That doesn't mean she's not paying attention. Luckily, I know she's paying so much attention that she knows that I don't mean that she's not paying attention. I'm not, anyway, whatever. Okay, I take it back. I take it back. Okay. Now, let me be a little more specific. Everything I just said is what an integral is. As far as I'm concerned, we just invented the integral, or we just constructed the idea of an integral. We still don't know how to solve it, but it's just a notation for what we want for calculating work. But now, what do I mean by a path integral? A path integral is a specific kind of integral. A path integral is when you integrate, when you have some function, in this case, force, when you have some function of x, sorry, you have some function of space, of position in space. When your products are specifically dot products, and when the dot products are specifically between the function itself and literally an interval in literal space, like as opposed to time, or as opposed to electric field or something else, if literally your independent variable is space, is position in space, and if literally your products are dot products between the function and the space itself, then that's called a path integral. In other words, when you're integrating, when you're adding up the effects of some function along a one-dimensional region of space, when you're not just, in other words, whenever we do any integral at all, we're always imagining ourselves walking along the x-axis of a graph and asking how high is the graph at that x value and multiplying the two and throwing it back. We're always imagining ourselves walking along the x-axis of some graph, no matter what. But a graph is a representation. We always walk along the x-axis of a graph because we're always imagining ourselves tallying up the independent variable, whatever it is. It could be positions in space. It could be moments in time. It could be velocities, whatever. Everything I've said about integrals thus far applies to whatever your x-axis is, whatever your independent variable is. But I'm now saying if specifically your independent variable actually is positions in one axis of space, if your independent variable really is x in the physical sense of x-axis, and if the products you're doing are actually dot products, then the integral, the entire integral, is called a path integral. So ultimately, I'm saying that is the case here with our specific physics integral that we're looking at. Work, just in sum, work is not just only an integral. Specifically, I'm saying work is the path integral of force. It is force dotted with displacement summed over a continuous interval. Okay, just that's a vocabulary or whatever. All right. So when it's work is the integral of the dot product of force with displacement. The word for that whole package of integral and dot product is called a path integral. It's a mathematical thing. There's many path integrals in physics. We'll see others, but I think work is the most vivid, fundamental, clear example of a path integral. Okay. Now I'm just looking at the time. Oh, we got time. Okay. Wait, actually, since we do actually have time, we're doing more, but we do have time. I just want to check in with you. I'm going to say one thing and then I'm going to ask you a question. I want to make it clear again. Nothing I have said so far has anything to do with how to solve an integral. Nothing I've said even proves that we even could solve an integral. Like, I don't know what the answer is to an integral yet, but I'm just saying this is what an integral means so far. And I'm saying it means something like, okay. Like, one way you'll know that you know what, so what you want to know right now, what you want to check with yourself is, are you following me? Do you feel, the question is, I mean, I'm not asking you, the question to ask yourself is, do I feel like I sort of know what an integral is? Not what to do with it, not how to solve it, but do I sort of see why it ever comes up or what it is? And again, what I'm saying it is a continuous sum of products. It is sigma taken to the limit. I mean, it's, yeah, It's sigma of f of x times delta x. Take it to the limit where delta x goes to 0. That's what I'm saying it is. If you can hold one way to know if you're sort of following me is if you can hold those words in your mind, and if they mean something to you right now, what I want to ask is this: in a moment, raise your electronic hand. Okay, first of all, okay, just raise your electronic hand if you can hear me right now. Just period. Raise your electronic hand if you can hear me at all. Like if you're with me at all. Cool. And keep them up, please. Keep them up. I'm going to do this actually seriously. Like just keep up your hand if you are with me at all right now. Like if you're in the room paying attention to me at all. Oh, 2 hands. That's awesome, Estrella. Thank you. No, that's cool. You can do that. I like that. Wait, so I'm going to be rude for a second. Like you've been Adan, Kirsten, Arini, like Rashman. Are you with me at all? Like, okay, I feel terrible that I just did that, but just keep your hand up if you're with me. Yeah, okay, cool, cool. Thank you. Okay. Just somehow indicate if you are paying attention at all at this moment. Well, it's okay. That's thank you. You've been, I totally, so all right, most of you. Okay. And now you can put your hands down. Now here's the question to ask yourself. If, just sort of be honest, if I walked up to you right now, or if we had a test or something like that, and you put away all your notes, if I asked you in your words in sort of your words, to explain what an integral is, here's what I want to know. You don't have to do it. You don't have to do it now, but here's what I want you to honestly tell me. If I asked you to explain what an integral is, could you do it without using any word like antiderivative? Raise your hand if you feel like, and I'm not going to make you, but I want to know honestly, do you feel like if I asked you right now to explain what an integral was, or on paper, could you do it in a way that did not use the word antiderivative? Raise your hand. That's Amanda. Thank you, Amanda. That's awesome. Now that's one person. Thank you, Amy. Thank you, Evan. Thank you, Kevin. Of course, there's no way of me proving that. I mean, okay, that's 3. Now people are being a little bit more attentive. That's interesting. Raise your hand if you could explain what an integral is with the word antiderivative. Interesting. Right. Raise your hand if you could look at your notes right now. If it was open notes and I asked you to write on a piece of paper right now to explain to me, but in English, but your notes were open. If I asked you to write down on a piece of paper in English, like without lying, what an integral was, could you do it right now? That's more people. Keep them up. Keep them up, please. Okay, that's a lot. Okay, cool. I believe you. Okay, cool. And you feel like you would sort of, even if you had to look at your notes, would you sort of feel like you understood what you were writing? Like now I'm just sort of asking, right? Like, yes, kind of, maybe face. Like I'm like, this is where, okay, Katya's being, okay, that's honest, Katya. Oh, Savannah, I like that. Okay. And Amanda, I'm just looking at faces that I can look at. I mean, Katya's giving me an honest face. I mean, okay. I mean, that is your challenge right now. Okay, thank you. I appreciate it. I mean, I think you're being on. I mean, I'll just say one more, because we're going to move on. Like, I just want to be, we're going to keep going. I mean, it never just sinks in all at once. And I do appreciate the honesty. And again, look, I think this is a really cool concept. I think we need it for physics. I think at a certain point we have to deal with it. And then you have been dealing with it for semesters. I'm trying to walk a fine line here as always in saying, look, on the one hand, integral is a deep enough thing that I don't believe anybody that thinks that anybody who says they get it the first time, they're kidding themselves. Honestly, it's deep enough that it takes a lot of thinking and a lot of repetition to get it to increasing layers. I want you to get it more. Oh, here's my last question. How about just this? Raise your hand if you, and you can put your hands down now. Sorry. Last question. We are going to go on. Just raise your hand if honestly, thank you. You can put your hand down. Dave. Oh, unless you have a question. Wait, Dave, do you have a question? Sorry. Or are you out of the room? Wait, Dave, are you good? Do you have a question? Or are you just keeping your hand up? Or have I lost you completely? Oh, this is so awkward. Okay, thank you. Okay. Last question. But this is like an ass kissy question. I mean, this is like, I'm not going to, no, don't raise your hand for this. I'll just ask yourself in your heart, do you feel like you see anything about the integral now a little bit more than you did before? You don't have to tell me, because then that's just like an ask-issy thing too. But like I'm trying to get you to see it a little bit differently from what you saw before. And my main goal right now, we're going to move on in a second. My main goal is I want you to understand that the integral is a thing that means something, whether or not you can solve it. There's a difference between a triple equal sign and a double equal sign. Like, I know that a lot of you have done a lot of integrals, but like, let's separate that from whether we understand what they are. And more specifically, what I'm trying to say right now is an integral is a continuous sum of products. And that in itself has nothing to do, with U substitution or integration by parts or power rules or any other procedural rules, nor does that have anything to do with antiderivative. It is just a thing. It's just a saying. If I wanted to know the work done by a force that was continuously changing throughout some value of x, like such as the force called negative kx, if I wanted to know the total work, the total accumulated effect of this force throughout this huge displacement, what I would want to do, I would want some kind of procedure that would allow me to divide the whole x into all these little infinitesimal chunks, each of which had a different f value, and somehow add up all the f times dx's for the whole thing. If I could do that, I would know the number of joules of accomplishment that the spring had done to the mass. By the way, I really care about that because ultimately what that's going to mean is I would know the number of joules of energy that the spring had given to the mass. Like, that's why I ultimately care about all of this. So what I'm saying right now is the integral would be the way of expressing that idea if only I could actually solve it. So now the question comes up, how can we solve integrals? Like, how do we do integrals? How can we do the integral of negative kx dx, like from x1 to x2? If I could do that, I would have the work done by the spring. Well, first of all, sorry, I think it said on that page, but I didn't read out loud. But yeah, so first of all, it says on this page, let's make it clear, not all integrals are solvable. In fact, the overwhelming majority of integrals that ever come up in circumstance are not solvable. They're not automatically solvable just because we want them to be. Second of all, when they are solvable, different integrals take different techniques and different tools to solve. There's not just one algorithmic procedure for solving integrals, unlike with differentiating there is. Like, when you look at an integral, you can't tell immediately necessarily without a lot of trial and error. You can't tell whether it's solvable or not, or by what method. So let me also just say again, if you ever felt sort of comfortable with taking derivatives, but then you got uncomfortable with integrals, whether you admitted it to yourself or not, if you felt a little bit more comfortable with derivatives than with integrals in calculus, please know that you are not alone, and please know that you're not crazy. That is totally the nature. It's not because you studied one and you didn't study well for the other. Derivatives are an algorithmic, like closed linear black and white procedure. And pretty much any continuous function, well, I don't want to say that, but functions in general, if they're continuous and they're recognizable, they're generally differentiable. And if they are differentiable, it's clear right away what procedure you would use to differentiate them. Integrals are more like solving puzzles, and you just get used over experience to different techniques that do or do not work under different circumstances. So integrals are intrinsically a harder, there's more of an art to the math of integrals than there is to differentiating. So if you've ever felt a little bit like fuzzy with them, that's not you, that's the nature of the beast. But here are some really important, here come now in the 16 minutes, some really important observations and tools we can use for solving integrals, at least the ones that we need for this class. So first of all, I'm changing the view again. Okay, first of all, like case number one up here, the so-called definite integral from x1 to x2 of dx, right? Which secretly is like if all integrals are a continuous sum of products, and the product is always, sorry, this all assumes We're assuming we've got some function of x. Y is some function of x. And an integral always is a sum of the products of f of x with an infinitesimal walk in x called dx. To integrate from, so remember, we no longer have the counter. We no longer have the index counter. We're not dividing into finite countable chunks. We're smoothly walking from the beginning of our x interval all the way to the end. So we start at the very first value of x, and we go and we keep adding up all of these products until we get to the last value of x. That's called a definite integral. Let's start with the most straightforward definite integral I can think of. Let's start for the case where f of x is just equal to the number 1. Like, where no matter what you plug in for x on some graph, you always get back the value 1, which is like a horizontal line in this graph. So we're looking at the integral of 1 dx. Well, by definition, the integral of dx, of 1 dx, is simply equal to x, not because of any rule or anything, but just because of what I'm saying integrals mean. To integrate is to walk a little bit of dx, ask what is the value of the function at this little bit of dx, multiply the two together, throw it in your bag, and then walk to the next dx, multiply them together, throw it in your bag. So you walk a little dx, and this rule says, take your value of dx, your little fraction of the total amount of x that you're walking, take your little fraction of x, multiply it by 1, put it in your bag. So like if we were doing work and we were walking 100 meters, it's like you walk one little infinitesimal meter, multiply it by 1, throw it in your bag. Then you walk to the next, take your next infinitesimal meter, multiply it by 1, throw that in your bag, and keep walking until you get to the end of the 100 meters, like the very last value, where x equals 100 meters. So if you add up all of the little infinitesimal fractions, all the little infinitesimal parts of this whole range of x values, what do you get? You get the whole range of x values, right? The integral, the continuous sum of all the little pieces of x gives you the whole x by definition of the procedure, right? So the integral from x1 to x2 of dx necessarily equals x. But what does that means? The value of x from the beginning all the way to the end. Like, so if you were walking in space, if you were walking from the 0 mark all the way to the 100 mark, you would say you walked 100 meters, 100 minus 0. If you walked from the 1 meter mark, all the way to the 101 meter mark, you say, oh, I ended up like what's displacement? Displacement is final position minus initial position. You would say, oh, I ended up at this place called 101 meters, but I started already at a place called 1 meter, right? I didn't start at 0, I started at 1. So I'd say 101 minus 1 equals 100. In other words, to evaluate the full value of x, you plug in the final value of it and you subtract from it the initial value of it. Just like displacement is final position minus initial position, or rise is final y value minus initial y value, right? So I'm saying by definition, if you do the definite integral from x1 to x2 of dx, you get x evaluated from x1 to x2. And what does that mean? It means literally the value of x2 minus value of x1. That is what the integral of dx is. It's just x. And I know you all knew that, but I'm just trying to, but if you believe that, so the integral of 1 dx equals x. Sorry. Now I know you knew that, or I think you knew that. But now I'm going to take it one step further and say, well, given that, what if, like, oh, there goes my board. Sorry. Hold on a second. And we've got 11 minutes. Hold on. Okay. Okay. Notice again, notice whenever we integrate a function, right? You integrate a function, and then if you want a number, you plug in values into that function, right? A function is something where you plug in one number, you get out a different number. An operation like integration is you plug in a function, you get out a different function. Like we're plugging in 1 we're plugging in the function 1 and we're getting out a different function x. If we want numbers, then we plug numbers into that function to get new numbers, right? So I'm saying whatever you integrate, it's always some function of x times dx. Well, what if that function that you're integrating happens to be that thing that we know from calculus to be known as the derivative of y with respect to x? Like we're assuming, right? Remember, we're assuming we have some function y is some function of x. Remember, if we picture a function of x, like we picture some graph where f of x is on this axis and x is on this axis, the slope of the line connecting any 2 points on a function, the slope of the line is delta y over delta x, the rise over the run, right? If you take the limit as, and remember, delta is small but finite difference, delta is small but finite difference. The slope of the line connecting any 2 points on any graph is delta y, like y2 minus y1, over delta x. If you take that to the limit, if you shrink the 2 points so close together that delta x is as close as it can be to 0 without actually being 0, if you bring the 2 points so close together that they're as close as they can be together, they're immeasurably close together, but still not quite just 1 point, the slope of the rate of change between those two super close by points is the rate of change at one little moment in the graph. The slope is average rate of change, delta y over delta x, but the instantaneous rate of change, delta y over delta x in the limit as delta x goes to 0, is what we call dy over dx, right? dy over dx is just slope, is just rate of change in the limiting case where we're looking at change between 2 points that are so close together, they're immeasurably close together. They're as close as they could be without actually just being 1 point. The rate of change at such a small infinitesimal interval is what we call the derivative, right? Derivative is instantaneous rate of change. It's not slope of a line connecting 2 points, it's slope of the tangent line to the curve at 1 point, or to the function at 1 point, right? So one thing, I'm slightly sidebarring, but slightly not. One thing I'm just reminding you is when we say derivatives are dy, when we say the derivative of y with respect to x is dy over dx, again, let me say that is not arbitrary notation. That's not black magic. That is literally saying, wait, who's here? Is it my next class? Oh, no, okay. When we say that the derivative is dy over dx, we're literally just saying that slope, dy over dx is just slope, but taken to the limit as the run is gets infinitesimally small. So derivative is limiting infinitesimally small slope. It's instantaneous rate of change, and it's a function. A derivative the derivative of a function spits out some function. So I'm saying now, and we're just about done. Now I'm saying, I've said all this stuff about, I'm just trying to get the board back. Where's my board? Hold on. I know you can see it, but like 1 second. It's coming. Oh, so right at the crucial moment, of course. Yeah, here. Okay. Okay. What I'm saying is, what if now? So we've been talking about integrals all this time. Here's integrals over here. Continuous sum of products, area under the curve, if you like. That's integrals, continuous sum of products. Then I just remind, and they have a dx in them because they're continuous sum of function times differential. Remember, dx, any d thing is a differential, an infinitesimal difference. So we have integrals over here, which are continuous sums of products of functions with dx's. Then over here, I'm reminding you this other thing from calculus, which I think probably many of you are a little bit more comfortable of. We have this instantaneous rate of change thing over here, the derivative, right? Over here is this derivative. A derivative is not a differential. A derivative is a ratio of differentials. It's a differential rise per differential run. A derivative is how much the curve goes up per every amount it goes over in the limiting case where we're just looking practically at one point on the curve rather than the interval between two, right? So over here we have integrals, continuous sums, and over here we have derivatives, instantaneous rates of change, areas under the curve, slopes of tangent lines, two unrelated things except that they somehow both deal with infinitely small. What I'm saying is, since integration is something you do to a function, let's imagine for a moment that the function that we're integrating is itself a derivative. Just imagine. So I'm in case 2 here, and I know I'm watching the time. Just say we do in case 2, the integral from x1 to x2 of dy dx. Like, where did that second dx come from? It's always there in the integral, right? We're integrating function, like dotted with or multiplied by infinitesimal change in the independent variable. So say we're integrating dy dx. Well, look, the dx's seem to cancel. They seem to cancel there. And so then what we have is integral of dy. But we just said a second ago that the integral of dy is just y, right? The integral of dy, add up all the little sections of dy, you get y. What's my point? My point is, evidently, when you think of it this way, if you use this notation, if you take the notation really seriously, the integral with respect to dx of dy dx is just y. The integral of some function, the integral of a derivative of some function apparently just spits out the original function. I didn't see that coming. I wasn't saying that for the last hour and a half. For the last hour and a half, I was just saying integrals are continuous sums. Then I reminded you that a derivative is a slope of is an instantaneous rate of change. But now I'm saying if you take the continuous sum of an instantaneous rate of change of some function, evidently what you get is the original function. So evidently, double equal sign, what I'm saying here is evidently when you integrate, you unwind a derivative. When you integrate, evidently, it's not what it means, but apparently what's happening is it inverts a derivative. The integral is triple equal sign, the continuous sum of products. But what the integral apparently often is double equal sign is the inverse function of the derivative. This is known as the fundamental theorem of calculus, FTC. I know you all know it, but I'm trying to do this in a different order to make a huge point here. I'm saying it's a fundamental theorem. It's not a definition. The definition of the integral is continuous sum of products. But it turns out by theorem that continuous sum of products is equal to the antiderivative. So if you ever want to solve an integral, what this tells me is, if I ever want to solve an integral, I can often use this fact as long as I can solve an integral by doing derivatives backwards. What this tells me, what this part tells me, is that if I want to figure out the work done by a spring, if I want to do integral of negative kx dx, I don't know how to do that just by looking at it. But if I realize, wait a minute, the integral is the antiderivative, the integral is inverting the derivative, then I just say to myself, what function, if I differentiated it, if I use all my simpler differential derivative rules, such as power rule, what function, if I differentiated it, would give me kx? And the answer is 1f kx squared would, right? If you take 1f kx squared and do the derivative, you multiply the whole thing by the power of 2, and then you bring down the power to the power of 1. So 1f kx squared times 2, bring down the power, you get kx. Evidently, the integral of kx would be 1f kx squared, because the derivative of 1f kx squared is kx. We have 1 minute. Now, again, everything I just said, in a way, you know, I know you know, but I'm trying to put it in a different order to put perspective. I'm saying, like, bottom line, when they taught me that the integral, when I got to the fundamental theorem of calculus and they said it was a big deal and it was fundamental, and they taught me that the integral is the antiderivative, I was like, that's a fundamental theorem. I don't see what the big deal is or what you're even saying, because from day one, you've been telling me that the integral was the antiderivative. Of course, the integral is the antiderivative. That's what you said it was. So why is it exciting to now say it's a theorem that it is? What I'm telling you is, no, that's not what it is. The integral is not the antiderivative. The integral triple equal sign is the continuous sum of products. But it turns out that the continuous sum of products, for some strange reason, is equal to the antiderivative. It turns out that the area under the curve is the slope of the tangent line backwards. I didn't know that, but if you just look at this notation, it seems evident that that's true. So to solve integrals, we do derivatives backwards, such as the integral of kx is 1/2 kx squared. That's all I got for today. That's it. I have a class coming in. If you have a quick question, I'll totally answer it, or we'll make an appointment. But other than that, I'm going to go in 2 minutes. But you guys have been very patient. I hope this helped at all. We'll keep going. Blah, blah, blah. Blah, blah, blah. Have a good day. Yes. Have a good day. Thank you.
Have a good day.
Have a good day. Have a great day. Stop the recording.